Yeah. Don't forget to bring your lumpy space princess to class. Yeah. Of like the videos or the graphic novels. Okay. Yeah. Yeah. All right. Hello, everybody. Welcome back to Comp 3430 Operating Systems. Let's get started. I mean, there's a test tomorrow. I'll announce that there's a test tomorrow. You should have received emails. You all got emails from me? Good, 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 good. Okay, great. I mean, I bring the seat assignments to class as an Excel spreadsheet, so like I can find out who sits where if there's an emergency, but it's a lot easier if everybody just knows where to come and sit. I posted on the course webpage like the map of the room with the seat numbers, so you can see that now and get a sense of where you're going to be sitting tomorrow, but I'll also just put it on the screen when you're coming in the classroom tomorrow. I'd like to get the test started as soon as possible. I am going to come early to class to put everything down, and I'm going to ask everybody to leave when I set everything up. But you can like leave your bags and whatever if you want in the room. It's just me. You can trust me. I'm not going to rifle through your stuff. And then I'll ask everybody to come back in, and then we'll just try to get started at 12:30, like right away. Try to get started right at 12:30. When I run tests, I usually put like a timer up on the screen, and I don't mean to do that in a nerve-wracking sort of way, but it stops me from having to shout, like there's 10 minutes left and there's 5 minutes left, and it stops me from having to go around and ask people asking what the time is. So I don't think there are any clocks in this room. There are no clocks in this room. Wow, okay, so there's no clocks in this room other than on the screen, and it's obscured right now. So I'll put a timer up on the screen so that you can see how much time is left. You only need a pencil or a pen to write, so like no calculators or anything for the test. I think that's it. Are there any urgent last-minute questions that anybody has? Just test nerves, yeah. Okay, all right. The only other thing I wanted to mention was about the lab. So one of the questions is asking you to run strace to try and determine what differences there might be between using pthread mutex lock and using your own lock implementation, the primitive, the atomic primitives implementation. One thing that you can do when you are doing this is if you're going to use strace, to use strace this -F for follow forks. So this option here, -F for follow forks. And what this says is that it is going to follow the child processes that are made with the clone system call. And if you remember when we were looking at the performance of threads versus processes, threads are using that clone system call. They're using that clone system call. So using the -F option here will give you possibly different output than just running strace with no extra options. I'm telling you this verbally, it's not in the lab document. So like if you want to just do what's in the lab document, that's totally fine. But you're going to get more interesting results if you use the -F option to take a look at that. Because I published the lab so early, it's fine. If you don't use -F, no problem. If you don't use -F, no problem. Report the results that you find without using it. If you do use -F, great. I hope that you learned something from that. Yeah. And I think that's it for announcements, other than a reminder that Friday the class is scheduled in Aurora, but there is no class and I will not be here. This will be a room that's assigned to us if you want to come and work someplace quiet. There's like, I don't know, there's only like 4 plugs in this room, so it's not exactly a great place to work, but it will be quiet if you want to find a quiet place to work on Friday. All right, I think that's it for announcement-like stuff. So let's kind of get started with the task for today. So by the end of today's lecture, what I want you to be able to do is compare and contrast preemptive and non-preemptive multitasking. So we're going to start taking a look at some scheduling policies and try to compare and contrast scheduling policies. And one of the properties of different kinds of scheduling policies is that they can be preemptive or non-preemptive. This is a place where that preemptive keyword is overloaded. So we talked about no preemption in terms of locks and deadlock. Preemption here is the idea of being able to forcibly take something away, but the thing that we're taking away here is access to the CPU. So a job is running on the CPU. If we preempt it from running on the CPU, we're forcibly taking it off of the CPU. We're switching to something else. Non-preemptive multitasking is kind of the same as what we were thinking about with deadlock and mutex trilock. I'm going to voluntarily give up this thing that I'm holding right now. Non-preemptive, I will volunteer to give up access to the resource that I've got. Preemptive, I am forcibly having it taken away from me, and I don't have a choice whether I want to or not. So I want to take a look at a couple of different scheduling policies in relation to this and how they behave differently. I want to be able to compare and contrast different scheduling policies. We're going to specifically be taking a look at measuring the performance of different scheduling policies on a workload to see how those scheduling policies behave differently. And time permitting, evaluate the performance of scheduling policies. So I want us to be able to evaluate the performance of these scheduling policies. So this is turnaround time and response time and fairness. I want to be able to measure whether or not these scheduling policies are fair. And then time permitting, I'll step through the condition variables code. I posted it on the course webpage. It is, I believe it's fairly straightforward to read, but I'm kind of a biased person in that sense that I'm the one that wrote it. So it's kind of unfair for me to say that it's easy to read because I'm the one that wrote it. So if we have time at the end of the class, that's what we will do, is take a look at that. The other topic that we had for this week was disk and I/O stuff. We will do that a little bit at the beginning of next week. And for context, the purpose of the disk and I/O stuff is to give us a little bit more kind of information about why file systems are designed the way that file systems are. How does hardware actually affect the design of file systems? That's why we look at that, that part of the hardware, where most of what we're doing is spending time in the software side. All right, so we've got an operating system. We've got processes, we've got threads. We have this idea of being able to switch between tasks, whether they are processes or threads within a process. There's a part of our operating system that's making the decision about which task gets to go next. And the part of our operating system that's deciding which task gets to go next is this scheduling machinery. I'm kind of describing two different parts here as one big thing, but there's two separate parts. The first one is the scheduler itself. The scheduler itself is the piece of code in the operating system that is making a decision about which job goes next. The idea here with the scheduler is that we have a queue of tasks. They might be threads, they might be processes, they might be some other kind of primitive that we don't talk about here, but they might be something else, but they are a task, they are something that needs to get access to the CPU. Our scheduler here is a black box. And we give as input to the scheduler this queue of tasks. These are the things that need to be run. And the scheduler's job is to go through that list of tasks, apply some policy, and then say, this is the next one. This is the one that gets to go next. The other half of scheduling is the dispatcher. So two parts. Queue goes in, one single task comes out based on what the scheduling policy decides should be the next job. And then once we've decided which job gets to go next, it's the dispatcher's job to take that task and switch it onto the processor. So going through the process of context switching between two processes or two threads or two tasks. It's the part that's taking all of the stuff that we've got in context and switching tasks between tasks on the CPU. I've got a design question here, and I'm going to just give you 10 seconds to think about this, and I'm not going to answer it right now, but I'm going to answer it in the form of a quiz in just a second. So take 10 seconds, think about why these two things would be separate. What would be advantageous? Why would we want to have these two things be separate from each other? And what are they actually doing? Okay. My hint to you is how much of the hardware does each of these actually have to know about? How much of the hardware does each of these actually have to know about? That's my hint. Let's have a quiz. Is this a peach or an orange? The song Peaches, 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 Peaches happens a lot at my house right now. If you've seen the Mario movie, have you seen the Mario movie? Please tell me you've seen the Mario movie. Some of you have. It's okay if you haven't, I guess. I guess. It's a good movie. It's fun. Bowser is played by Jack Black, and there's a song that he sings about Princess Peach. It's just peaches, 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 and my kids are just constantly singing this song, and it's both adorable and incredibly annoying. All right, let's get started. 6 questions. They're all about scheduling policies. All right, good. Perfect. A scheduler can schedule tasks without having to know how to switch tasks. The scheduler, in our kind of big context of an operating system here, is dealing purely in abstraction. A task is an abstract thing. It's this idea, it's this unit of work, it's a queue of structs, and that's all it really needs to make decisions about. Queue of tasks go in, one single task comes out, which is the one that gets to run next. The dispatcher is that piece of code that's going to be platform specific or architecture specific. So it has to do context switching. It has to know about all the kinds of registers that need to be saved into a structure on the PCB or the TCB. And it needs to know how to restore those registers from the PCB or the TCB. A scheduler can do its job without having to know anything about registers. It doesn't really have to care anything about registers because it's just picking which thing gets to go next. The dispatcher is going to have to know how to do all of that stuff, but it doesn't pick what gets to go next. It just gets told, this is the one that is being switched on right now, please. Pizza Pops. I'll read this out loud. What's the main additional support requirement for preemptive multitasking compared to non-preemptive multitasking? All right, okay. So this is kind of a divided thing. That's okay. Preemption, remember, is this idea that we have to be able to take control of the hardware again. We must be able to take control of the hardware again. The operating system is just code. It's just code all the way down. It's C, and then C, and then C, and then assembly language. And then binary? I don't know. Then it's code, but it's just code all the way down. Once a piece of software starts running on the processor, other software can't take it back. It can't be like, okay, you're running, and I'm going to run somewhere else and also run at the same time. It's not something we can really do. In order for us to be able to forcibly take control of this thing back, we have to have hardware support. We have to have our hardware know how to call into the operating system and say, okay, a certain amount of time has elapsed. Now it's your turn to run on the processor, and you can make a decision about what gets to go next. Operating system support, context switching. This is actually necessary for both kinds, preemptive and non-preemptive. Our operating system has to be able to switch between tasks, whether the tasks have had the processor forcibly removed from them. You don't have a choice, I'm taking the processor back, or you are voluntarily giving up the CPU. So making system calls, software support, or yielding, so voluntarily giving up access of the CPU back to the operating system. So we've got this idea of yielding, but this is also going to be making system calls, asking the operating system to do something on our behalf. Whether we have taken the CPU back or we have given up control of the CPU voluntarily, we have to be able to do context switching. So in order for us to do preemptive multitasking, forcibly take control back, we have to have help from our hardware. Our hardware must be able to provide some kind of support for us to be able to do that. It's okay with everybody? Any questions? All right. Pizza Pops. What's the main difference between shortest job first and shortest time to completion first? These are two scheduling policies. We'll look at more at these today. All right, good. Shortest time to completion first is a preemptive scheduling policy. Shortest job first is a non-preemptive scheduling policy. So quick overview, shortest time to completion first, jobs come in, and we can frequently decide which is the one that has the least amount of time left. If there's one that has less amount of time than the one that's currently running, we should switch to that task and let it finish first. Shortest job first is whichever one comes in first gets to run first. If there are two jobs that happen to be there that are waiting to run that have a difference in the amount of time that's left, shortest job first will choose the one that is shortest in total amount of time and let that one run first, but it runs to completion. Shortest job first knows the amount of time remaining for a job, and shortest time to completion first does not. This idea of knowing how much time a task has left is one of the unrealistic assumptions that our textbook is talking about. This isn't really something that we can know but it's something that we can make assumptions about so that we can reason about these different scheduling policies. And in the case of both shortest time to completion first and shortest job first, we both kind of know those things. We know how much time there is left in a job in the set of unrealistic assumptions that we have for the textbook. Shortest time to completion first incorporates I/O and shortest job first does not. The first time that we talk about doing I/O is in the round robin scheduling policy. But shortest time to completion first, this isn't really a major difference between the two of them. The main difference is that it's preemptive versus non-preemptive scheduling policies. Okay, good. Okay. Well, Pizza Pops. Why is knowing how long a job takes to complete unrealistic? Good, excellent. It's hard to count instructions in a program. Well, that one, that could be interpreted as a reasonable answer. But I would answer that by saying you can just run your compiler to get the assembly language instructions and then just count. Use something like WC to count how many lines there are in it. Programs all complete in the same amount of time. That would be I don't know what kind of a world that would be. We can easily find out how long they take with Hyperfine. We can run a job and see how long it takes to complete, but that assumes that it finishes at all. Knowing how long a job requires to complete requires solving the halting problem. Yeah, and we can't do that. At least as far as we know, we can't do that in a reasonable amount of time. So yes, good, great. Pizza Pops. I really want Pizza Pops to stay on. How is the multi-level feedback queue similar to lottery scheduling? These are the two kind of most complicated scheduling policies that are described in our textbook. All right. They are both indeed scheduling policies. Yes, that's a true statement. That is a true statement, but it's not the best answer in this case. Both use priority queues in their implementation. Again, yes, that is a true statement, but it's not the best answer in this case. Both consider I/O in their implementation. Multi-level feedback queue explicitly does at a certain point, but otherwise does not. The lottery scheduling one also does consider it, but does not really have, this isn't really the best answer. Both have the concept of priority in their implementation. So this is the best answer in my mind. Both of them have this concept of priority in their implementation. Some jobs are going to be able to get in front of other jobs based on what priority they currently have. While I'm here and while I'm thinking about this, I'm going to verbally say that you are being assessed on the multi-level feedback queue in assignment 2. You were being assessed on that in assignment 2. Please take that hint. Please take that hint. Yes. Are there any questions about this question? Okay. All right. Pizza Pops. Ohm has moved up from like way down up to the top. That's very good. Here's the last question. How do you assign tickets in lottery scheduling? Okay, all right, okay. Yeah, the answer here is, I don't know. Let each job decide how many tickets it gets. That does seem like a reasonable choice to make. I'm going to say that I've got 100 tickets. How many tickets do you want? Okay, how many tickets do you want? Okay, I'm surprised by that, but okay, how many tickets do you want? Just one. How many do you want? 50, you? A million. Okay, I don't have a million tickets, I only have 100, so I'll give you 100. Okay. I'm surprised. I'm really surprised that some of us are so generous by only asking for a few tickets instead of all of them. Because if we let jobs decide how many tickets they get, they could just ask for all of them. Every single one just asks for all of them. Implement tickets as NFTs and let jobs bid on them. I don't know. Maybe that would be a fun research project, but that's probably not a good choice for an operating system. All jobs get the same number of tickets. That actually does seem like a very reasonable choice. That does seem like a reasonable choice. The problem with that is that all jobs then are the same priority. They are identical in their priority. And so that means that every job is going to have the same priority. So we're just going to go back all the way down to round robin, basically, if we let everybody have exactly the same priority. If we separate the concept of tasks, processes, and threads within a task, a process could possibly make decisions about how many tickets each thread gets. That would be reasonable. That would be very reasonable to make a decision about. But very generally, just give everybody the same number of tickets is not the greatest choice. All right, let's see. Oh, okay. Semicolon dash. Is this, I don't know, I can't tell if this is an attempted happy face or if it's an attempted SQL injection attack. I can't decide. Congratulations, semicolon dash. Are there any questions about the questions that I've got here before we move on to actually applying scheduling policies here today? All right. So I've been signed up for Kahoot for a really long time, and they are starting to use what I consider to be fairly like dark patterns in terms of like trying to push me to buy more. Every time I log into Kahoot, it's like pay $18 a month, which is that is not a reasonable amount of money to pay for Kahoot. Pay $18 a month and upgrade so that you can get this other kind of quiz, which is just, I don't really want to do that. I think I'm paying like $8 a month right now, which is still a lot. But now I see this ad showing up here, which is just like, I have no idea what this is. And it's starting to really make me reconsider using Kahoot. So if you really, really think it's fun, let me know so that I can keep justifying the cost of $8 a month, but I may not continue the subscription. The problem is that I've invested so much time in making these Kahoots. There's so many in my library that it's going to be hard to give it up. I have digressed pretty far. Let's get back onto topic. I would like us to go through the process of mechanically applying some scheduling policies and then making comparisons about their behavior, making comparisons about the type of scheduling policies that there are, measure their performance, and see how they work on a specific workload. We're going to look at 4 policies, or as much as we can. We're going to look at first in, first out. This is a non-preemptive scheduling policy, and this is the simplest one. It is literally just a queue. It's not even a special kind of queue. It's just literally a queue of tasks. There's shortest job first, which is a slightly more complicated scheduling policy in that it is a priority queue now, but it's still just a queue, and it is also a non-preemptive scheduling policy. There's shortest time to completion first. This is a more complex one. It is a priority queue. It's a priority queue, but it is preemptive. It can actually take processes or tasks off of the processor. And round robin. Round robin is still sort of a queue. It's still sort of a priority queue, except it is rapidly switching between tasks as opposed to letting jobs complete their task. It's always going to rapidly switch between tasks. We're going to try to do each of these, and we're going to be measuring some things about them as we go through these policies. The performance things that we want to measure are turnaround time. So based on when the task arrived, so not when it starts, but this is more like me taking my mouse and clicking on this app. That's the arrival time. That's when I want to start, when I have asked for it to start in the system, and then when it actually finishes running, so when the job finishes. Arrival time is it has been added to the system. I've asked for it to start. Completion time is this job has finished. It's called the exit system call, and it has started to shut down. We're also going to measure response time, and this is more about based on when it arrived versus when we actually start to see something happening. So this is the difference between me clicking on this icon and being able to see the app as opposed to it actually finishing the job that it needed to do. I want to know when I can start interacting with this thing. What's the response time of the app? And I also want to know about fairness. If we were to take this scheduling policy, can we guarantee that every task that's in the system will eventually get time on the CPU? Can we say that with certainty? Or is it possible for us to get into a state where a task gets on the CPU and then never lets anybody else get on the CPU? Everybody else just kind of gets stuck out in the cold and they don't get to have the CPU for any amount of time. The way that we're going to do this is that I've got a template here. I've handed some of these out at the beginning of the class. I've got more up here. If you didn't get one and you want a paper copy of this, please feel free to come up and get one. If you're getting a paper copy, please grab 5 of those sticky notes. I've also got this up on the course webpage as this document. It's a PowerPoint document so that you can interact with it if you want. So you can take this off of the course website and do the same sorts of things that I'm doing. I'm going to give you about like a minute or a minute and a half to copy down these tasks up here at the top of the screen onto your sticky notes. You don't necessarily have to write down everything that I've got here, but minimally label them with their letters. So A, B, C, D, and E, and ideally label them with the remaining and arrival time. That's ideally, you don't have to write all that down, but ideally put that down. And I'm just going to zoom in a little bit up on the top just to start so that it's not this minuscule font. So take a couple minutes to do that, and then we're going to go through the process of looking at first in, first out. If you need a pen, if you want a pen, let me know. I've got lots and lots of pens. Feeling really nervous about the wind. because it was a terrible, terrible strong headwind biking in this morning, and I don't want to bike into a headwind on the way home. But it looks like it'll be okay. It will push me home. It will push me home. I'll leave this up here for 5 seconds more. Okay, I'm not going to take this down. I'm just going to start zooming back out and then starting to interact with it. So what I want us to do is start to actually go through the process of applying some of these scheduling policies. I'm going to try to zoom in so that this is big enough. I want to tell you about what each of these different parts are, and then we're going to start working through it. So at the very top of this diagram, we have the incoming workload. These are the tasks that are going to enter our system at some point. We're relaxing one of the assumptions that the textbook was stating. And one of the assumptions that the textbook stated at the beginning was that all tasks arrive at the same time. We're not going to be assuming that for any policy. We're going to be assuming that tasks can arrive at any time for these policies that we're taking a look at right now. The tasks at the top, and this is where all of your tasks should start, is at the incoming workload spot. These are all of the tasks that are going to be added to the system at some point. We have one CPU on our system. There's only one CPU, only one physical CPU, so there can only be one running task at a time. So we can only ever have one sticky note in there. And when a task is running, so when our scheduler, we are the scheduler, when we've decided that this is the next task, we're going to put that task into the running task spots. If there are other tasks that have arrived but haven't started yet or are not running, they're going to go into this task queue area. So we're going to stick things in there while they are not running, but while they are still in the system. All of the tasks have a remaining time in them. This is how many units of time are left to complete that task. We're going to make the assumption that we know how much time is left. Once a task has 0 units of time left, we will move it into this completed tasks area. And then we're going to calculate those performance metrics after all of the jobs are done. After all the tasks are finished, we'll go through the process of starting to calculate the performance measurements. At the very bottom here, we've got current time and quantum of 5. Quantum is the same as time slice. These are synonyms. This is the amount of time that the task is going to get to run on the CPU before it is preempted in preemptive scheduling policies. The current time, I am going to be changing. I'm going to be the clock. I'm going to tick time. And we're going to all collectively try to make changes to the state of our system as we're changing the time that we're looking at any given time. So I'm going to start by saying that we're at time 0 at the very beginning. It's the very start of the universe. This is the start of the universe. And the policy that I want us to apply first is the first policy, which is, we're going to do FIFO first. First in, first out. Any questions? It's okay. Straightforward. Good, good. Okay. If you're taking software engineering, now we're also doing arts and crafts here. Yeah. So let's do FIFO. I'm going to start time. So I'm starting time. Our current time right now is 0. And so our task is to find out if any jobs have arrived in the system right now. Take a second. Move your sticky notes around. I'm going to move my sticky notes around up here. Task A has arrived in the system. It has an arrival time of 0. When a task arrives, we're going to say that in the same instant, so at exactly the same time, it will arrive. If there's no other task running, we're also going to say it starts. It just immediately starts. It doesn't go into the queue, or it temporarily goes into the queue for such a small amount of time that it's still at time 0. So task A then immediately starts running. It immediately starts running. And what we should do when a task starts to run is we would normally compute or to write down what the arrival time is, but that's already been written down for us, so we're good. There's nothing left for us to do at time 0. So I am going to change the time. The current time is now 1. Take 5 seconds. Do we do anything? That's the question. Do we do anything? Just quick thumbs up, thumbs down. We do anything? No, don't do anything. Don't do anything. Good. The time is now 2. Do we do anything? No, we don't do anything. The time is now 3. Do we do anything? No, we don't do anything. Time is 4. Do we do anything? No. The time is 5. Okay, do we do something now? Yes, we do something now. There's a couple things that we need to do now. The current time is 5. The time remaining, or the time that we had in total, was 5 units. Time has elapsed. I'm going to say that there's 0 units of time. And sorry, I forgot. We also should mark down that the first run for this one was 0 because it started at time 0. The completion time for task A with FIFO is 5. It finished as soon as it had nothing left to do, and its job is done. So I'm going to move task A now into this completed tasks area. It doesn't need to go back to the current task queue. It's finished. What else do we need to do? Just shout. We got to move B and C into the queue. Which order did they go in? B then C? Does it matter? They both arrived at time 5. I'm going to say it doesn't matter. We're going to make an arbitrary decision here. If 2 tasks arrived at literally the same time, they can't. They can't. I don't think anybody could do that. I don't think anybody could do that. But we're going to say that they both arrived at the same time. This is a queue, so we're going to keep them in the order that they have arrived in. There's no task that's running on the CPU, so we're still in the same instant. There's no task that's currently running on the CPU. So I'm going to put task B onto the running task spot, and I'm going to say that its first run time is 5. I'm going to record that. I'm going to shuffle task C over just a little bit so that it's kind of more clearly at the front of my queue. It has not started running, so we do not change its first run time. Its arrival time stays the same. Anything else? Good, that's it. Nothing left to do. So let's change time. We're at time 6. Do we do anything? Okay, this is getting tedious because we're just going to do a lot of nothing for a little while. So let's skip ahead. I'm going to skip ahead. We were just at time 5. I'm going to skip ahead to time 10. So we've done 5 units of time right now. I'm going to change time B to have 10 units left. Task B has 10 units left of time. Its arrival time was 5. Its first run was 5. It hasn't finished yet. It still has 10 units of time left to do. Do we do anything? What do we do? D arrives. Okay. So D is arriving in our system. Is there anything else for us to do? Should we switch tasks? Well, no, we don't switch tasks. So this is non-preemptive, so we're not going to forcibly remove this task. It's just going to run until it's done. I'm going to change time to time 11 now. And at time 11, we're moving task E into the current task queue. It just gets stuck on at the end. First in, first out. Last in, last out. It has not started running yet. The time remaining for task B has been reduced to 9 units. We've just changed it up by 1. We've got 9 units of time left. And there's nothing left to do. There's nothing left to do. We are not going to switch this task off once it's on the CPU. So I'm going to skip ahead. There's nothing left in the incoming workload. I'm going to change this to time 20 now. At time 20, task B is finished. There's 0 units of time left for task B. Because it's done, we should record the time that it finished. The time that it finished here is at time 20. It's finished, so I'm going to put it in the completed tasks area. And in the same unit, in the same instant of time, I'm going to take task C and I'm going to put it onto the running task. It's at the front of my queue, first in, first out. We need to start recording changes about this. Its first run is at time 20. This is the first time it got onto the CPU. The other 2 tasks that are still in the current task queue are just going to sit around and wait. They have to wait. I'm going to skip ahead 10 units of time because it would be a lot of me. No, we don't need to do anything. Thumbs down. Let's just skip ahead 10 units of time. Now we're at time 30. We do not ever switch off task C. We never switch task C because this is a non-preemptive scheduling policy. So it just gets to go until it is finished. At time 30, there are 0 units of time left for this task. Its completion time, then it's finished, was at time 30. And I'm moving this task to the done area, to the completed task spot. It's finished. We go back up in the same instant, our current task queue, FIFO, first in, first out, take task D. Its first run is at time 30. And then we'll skip ahead 10 units of time. We'll skip ahead 10 units of time. We're at time 40. There are 0 units of time left. It's finished at time 40. Move task D to the done area. Same instance, move task E. Its first run is at time 40. We'll skip ahead 5 units of time. Its completion time is at 45. It has 0 units of time left, and it gets moved into the done area. Okay. First in, first out is not exactly the most exciting scheduling policy. It's not exactly the most exciting scheduling policy, but we have now completed it. We've got this quantum or time slice here, but this is irrelevant for this policy. It doesn't matter what the quantum or time policy is because it's not a preemptive policy. We will never switch a task off until it is finished. We're going to answer the questions about performance from the bottom up, I think. Is this a fair scheduling policy? What do you think? Can I guarantee that jobs or tasks in general will get access to the CPU? This is not a fair scheduling policy. Oh, and it's even a little sad face. That was a happy accident? It was a happy accident. If we have a task that's just spinning in a loop here and going on forever, we're kind of going back to that halting problem thing. We can't solve the halting problem. We don't know how long jobs are actually going to take. But if code gets stuck in an infinite loop here, the only way that we can get control back is like hit the reset button and then start all over again. So this is not a fair scheduling policy because of that. Okay, so are we good with FIFO? Okay. I'm going to Control Z all the way back to the beginning again. I'm going to hope that the undo stack goes that far. It does. I'm grateful. I'm happy. Yes, thank you, LibreOffice. I'm back at the beginning here again. The policy that I want to apply this time is shortest job first. Shortest job first, again, is based on the tasks that are currently in the queue, which one has the least amount of time to complete in total. I'm going to go through the process of changing time. That's my job now, and your job is going to be to do the scheduling policy itself. Okay? Okay. So we are starting, I'll give you some time to reset yourself. Okay, we are starting at time 0. Time is 0. The system is starting. Do what you need to do. Good. Okay, I'm going to do it. I'm skipping a step here, and I'm just putting this directly on. It's first run at 0. I'm going to skip ahead 5 units of time. Take 10 seconds, do what you need to do. We're good? Okay, I'm going to do what I need to do here. This has 0 units of time left. The completion time is 5. It's done. Task B and C arrive. They are arriving at the same time. Last time we said it was arbitrary, but now we are choosing shortest job first. Shortest job first here is C. Its first run time is 5. I'm going to skip ahead 5 units of time, give you 10 seconds to do what you need to do, and then I'll do it. It's 10. Time unit's 10. We okay? Good, good. Okay. So I'm skipping ahead 10 units of time. That means that C has 5 units left. Task D is entering the system. Shortest job first is a priority queue, and its priority is based on how much time the task has to complete. Task D has less time than task B, so it gets put in front of task B in our queue. It sticks in front there. We're okay with that? We're good? Okay. I'm going to skip ahead 1 unit of time this time. Do what you need to do. All right. In 1 unit of time, task C still has 4 units of time left to complete. Task E is entering the system. Task E has the smallest amount of time remaining in the job, so it goes first in the priority queue. It jumps ahead of everybody else. Task B has been in the system for 6 units of time, and it has made no progress because it is the longest job. It is the biggest job, so it's going to run last no matter what. We've skipped through several quantums. We haven't switched tasks in those quantums. This is a non-preemptive scheduling policy, so we don't take a task off of the CPU. I'm going to skip ahead now to 15. So this is time 15. Take 10 seconds, do what you need to do. All right. Task C is now done. It's at 0 units remaining. It's finished at time unit 15. It's going to get taken off of the CPU, or it will give up the CPU because it's finished. At the same instant, task E is going to move onto the CPU, and its first runtime is at 15. Good, good, good. I'm going to skip ahead 5 more units of time. There's nothing left to get added to our system. Take 10 seconds. All right. Okay, task E now has 0 units of time left. It's finished. It only had 5 to start with. Its completion time is at time 20. It's finished. I'm going to move it into the done area, into the completed tasks section. Task D is the one that has the fewest number of tasks time remaining. So in the same instant, it gets put onto the CPU. Its first run time is at time 20. Okay. I'm going to skip ahead here 10 units of time. We're going to let task E finish. Go ahead. Okay. I'm going to say that task D now has 0 units of time left. Its completion time was at time 30. I'm going to move it to the done area. In the same instant, I'm going to put task B on the CPU. Its first runtime is at, whoops, sorry, this was supposed to be time 30. Its first runtime is at time 30. And then we'll let task B finish. So after 45 units of time, task B has 0 units of time left, and it has completed its task. Okay. Let's answer some more questions about this. So last time we only asked about fairness, and we didn't ask about turnaround time or response time. I'm going to answer the first question about fairness for you. I'm going to answer it on your behalf. This is a non-preemptive scheduling policy. It is not fair. It is not fair. We cannot guarantee that everybody will get access to the CPU at some point for the same reason that we couldn't before. If somebody enters an infinite loop, they will just keep running forever. In this case, when we know how much time is left, yeah, I guess we could consider them to be fair. This one we can't consider to be fair because it could always be that some shorter task will always enter the system just before a longer one gets to run, and it will always be in the state of being pushed to the back of the queue. So both with and without that unrealistic assumption, we've got this state of task possibly never getting to finish in this situation. The 2 measurements that we wanted to make about our tasks were turnaround time and response time. So after entering the system, how much time does it take to finish? After entering the system, how much time does it take to actually get started? So task A here, the response time is, well, it's great because it arrived at time 0 and it ran at time 0. The response time for that task is 0. There's the difference between 0 and 0 is 0, 0, 0. Task C, the arrival time was 5. The first run time was 5. So response time is great again for task C. For task E, arrival time is 11. First run is 15. Our response time is 4. It's okay. It's okay. Task D, it arrived at time 10. Its first run was at 20. Okay, well now it's 10. And task B is terrible. The arrival time was 5 and it first ran at time 30. That's 25 units of time that it was just sitting around waiting. Like we clicked the button and then we just sat there and waited and waited and waited and waited for that window to pop up and nothing was going on. Shortest job first can have terrible response time when you've got a task that has a long time remaining. So tasks that have really long times to remain are going to have terrible response times in shortest job first. The turnaround time is, it's reasonable. It's reasonable. So this is the same as the amount of time that was remaining for this. It took 5 units of time for this to turn around. This is completion minus arrival. So this is 10 units of time. This is 9. This is 20. Well, this is 40. This is 40. And that's significantly more than the actual task had to begin with. But fair enough. That's just what this policy is right now. All right. OK, are we OK with this? OK. I want to do just one more policy here. Just one more policy, because if we keep doing this, it's going to be really boring. It's going to be really, really boring. As fun as arts and crafts is, I'm going to revert back to my original state. I'm back at time 0. This time, what I want to do is round robin. We're going to do the round robin scheduling policy, and this one is a preemptive scheduling policy. I'm going to do the same thing. So our current time is 0. Take 5 seconds, do what you need to do, and then I'll follow you up. OK, so round robin. We are having task A enter the system through the current task queue directly onto the CPU. The first run time for this is 0. And it's not done, so we're not going to do anything. I'm going to step ahead here 5 units of time. Take 10 seconds. OK. Five units of time have elapsed. Quantum matters now. Quantum does matter. In this specific case, task A is finished. So in this specific case, it's irrelevant. We're going to come off the CPU anyway. Its completion time was at 5. And so far, with all of the policies, FIFO, shortest job first, and round robin, task A, it always just has 0 response time, 0 turnaround time, or 5 turnaround time, the amount of time that the task actually had in the first place. So for all 3 of those policies, the turnaround time is the same for that task. At time 5, we've got task B and task C coming into the system. Does it matter which order they go in here? Is irrelevant. It's irrelevant. It's irrelevant. Unlike shortest job first, we are not prioritizing based on how much time is remaining. We don't really care, so let's just order them by the task ID that we've got here. At the same instant, I'm putting task B onto the CPU. Its first runtime is at time unit 5. Task C just gets to hang out and wait. I'm going to advance time here to time unit 10. Take 10 seconds, do what you need to do. Are we good? OK. At time unit 10, we've advanced 5 units. Task B has 10 units left. We're subtracting from how much time was on that task. Task C is at the front of our queue. Task D is entering the system. And now we're at a quantum. We're at a time slice. We're going to boot task B off of the CPU. It's finished its time slice, so it doesn't get to have access to it. Our hardware is interrupting. It's giving us control again, and we're going to remove task C from the processor. Task B from the processor. So I'm going to take task B. In my round robin, we're going to priority queue here. It's first in, first out, but it's time slices. It's quantums. Task B gets shoved to the end of the task queue. In the same instant, task C is going to get onto the CPU. There's nothing running on it right now, so we're going to put task C onto the CPU. That means that its first runtime is at 10. The other two tasks are still in our task queue. They're just waiting around. Task B had some time, but it's not finished yet. Task D hasn't started yet. Task A is still done, and task E is still waiting to come onto the scene. Let's switch ahead here. Time units 11. Okay. Everybody moves up a little bit. The amount of time left for task C is 9 units. Task E arrives in the system. That's kind of it. That's all we can do right now. I'm going to skip ahead now to time unit 15. Take 5 seconds. Okay, all right. Task C is down to 5 units left. So it's finished half of the work that it needs to do. But now we're at a time slice, and task C is going to get kicked off of the CPU. It will be forcibly removed from the processor. Task C gets taken off. Task D gets to run. Everybody shifts over a little bit. The first run time for task D is now 15. What we can already start to see is that the response time for these tasks is better immediately. Round robin is improving response time for the tasks that we have in this system. Last time when we did shortest job first, task D, I think, just kind of like waited forever. Or task B, I don't remember which one it was. One of those tasks just got stuck waiting forever, and now everybody has had a chance, almost everybody has had a chance to get to the CPU at this point. Let's skip ahead to time 20. Let's do another quantum. We'll do one more quantum here, and then I think we'll call it for this activity. Okay. Task D now has 5 units left, but it's finished on the CPU. We're kicking it off. It's going to the end of the queue. Task B is going to get onto the queue. That is not what I wanted to do. Task B gets to go onto the CPU. Everybody else kind of shuffles down here a little bit. And at this point, I will leave this as an exercise for the reader. If you want to keep doing arts and crafts at home, round robin, I think you have the idea. I think you've got the idea of how round robin is being applied here. The primary difference between the other two things that we were just looking at is that round robin is a preemptive policy. We are switching tasks constantly throughout the system. Response time is going down because everybody will get a chance to get onto the CPU fairly shortly after they have entered the system, based on how many tasks are in the system. So if there's lots and lots of tasks, we're going to have to wait for a long time before we get onto the CPU. Considering what we've considered, thinking about what we thought about, in terms of fairness, is this a fair scheduling policy? If I put while one sad face, can we still guarantee that everybody gets access to the CPU? Yes, yes. This is a fair scheduling policy. is not the best scheduling policy, but it's a fair scheduling policy, where the other ones we couldn't consider to be fair because somebody could just get the CPU and stay there forever. This one guarantees, because of the queue that we've got, and because we are preempting tasks, that we can say for 100% certainty that everybody will eventually get access to the CPU. Yeah. So round robin it is a FIFO. It's first in, first out with preemption. So the queue is always going to be a FIFO in this case. In other policies, so like multi-level feedback queue, now we're starting to do priorities on top of FIFO. Yeah, and we move them up and down, exactly, based on what their behavior is. So we start thinking about what a task is actually doing while it's doing it. But for round robin, it's just pure FIFO with preemption. Yeah. Any other questions? Okay, cool. All right. I like this. I know that it's kind of tedious. I know it's a little bit tedious. I really know it's a little bit tedious, but it gives us the opportunity to like actually see these policies in action, as opposed to just thinking about them, a little bit. Scheduling policies like this, they are queues all the way down. They are queues all the way down. Operating systems, actual modern operating systems, have you done 3170 yet? Did you do 3170? Some of you? Yeah? Okay. Did you do red black trees in 3170? No? Some people say yes, some people say no. It might be based on the instructor. It might be based on the instructor. Some of the most complicated data structures in modern operating systems, like Linux, are red black trees. It's undergraduate level stuff. It's undergraduate level stuff. The fundamental unit in an operating system is the queue and the linked list. Yeah. All right. So I'm going to close my presentation here, and I'm going to switch now to my condition variable stuff. I've got a couple minutes left, and so I want to take a look at that. I just want to take you through this. This code is posted up on the course webpage. Condition variables and locks in terms of pthreads they're deeply interrelated with each other. We've talked about locks in terms of blocking and preventing concurrent access to a critical section. We're trying to avoid data races. You can have 1 or 0, but not more than 1 tasks or threads entering a critical section. Condition variables are more like signals for threads than just locks. They're more like conditions for threads, signals for threads than just locks. A condition variable has a mutex that's attached to it. It's still used to protect a critical section, but the difference between just locking and using a condition variable is that a condition variable is often used to say, hey, there's something available for you here in this thing, as opposed to me then just having code that calls the lock and just gets stuck and waits for it. In this code, I've got a special function here that's called getTID. GetTID is a system call, but it's not in glibc, so I've had to wrap it. So this is, for what it's worth, how you would invoke a system call without calling the corresponding function from your standard library. In this code, we've got a thread. The thread is going to acquire a lock. It's going to wait for a condition to happen and then suspend itself. With pthread mutex lock, remember, we acquire the lock, and what we're basically saying is that before the unlock, there can only ever be 1 thread of execution running in this code. The difference between this and pure pthread mutex lock is that once a thread calls this, once it calls pthread cond wait, it suspends itself and it unlocks the lock. It doesn't proceed. It goes to sleep, it waits, and other threads can acquire the lock. Other threads are permitted to acquire the lock. It releases the lock when you call pthread const wait, yes. So it goes to sleep and it releases the lock, yes, thank you. In our main function here, we've got two calls that are being made after we create all of the threads. There's pthread const signal and there's pthread const broadcast. We're overloading terms, and I hate that we're overloading terms, but I didn't design these libraries. I'm sorry. It's just, I don't know why they made these choices. Wait in this case actually means wait and go to sleep, but it's the thing itself deciding to wait and go to sleep. Signal here is kind of the same as saying signal in processes and kill, but we're sending messages, we're sending signals to other threads that are in our address space. In this main function, we create a bunch of threads. So we're creating 10 threads here. All 10 of these threads are going to acquire the lock one at a time. They will acquire the lock. One at a time, they will go to sleep and they will unlock. And then they'll just get stuck. They're blocked there waiting, sleeping, not doing anything. When I call pthread const signal, the idea here is that I'm saying, hey, there's work for you to do now. Please wake up. Pthread const signal will wake up exactly one thread and no more, just one thread. Pthread const broadcast will wake up all of the threads that are waiting on that condition variable. So pthread const signal says, hey, wake up, there's some work for you. Only one thread will wake up from this statement right here. One thread will wake up, and when it wakes up, it will acquire the lock. No other threads can enter that section. It can do what it needs to do and then unlock the lock. Anybody else that was waiting there is still waiting and sleeping. They're not going to proceed. With pthread const broadcast, we're saying, hey, everybody wake up, and then they will each take turns acquiring the lock, doing what they need to do, and then unlocking it. I'm going to quickly run this code. I've taken too much of your time, I realize. This code is calling pthread const signal. We start 10 threads. One of them acquires the lock. One of them is woken up by pthread const signal. It unlocks the lock, but everybody else is just stuck. They're blocked. They're waiting. If I change this code to use pthread const broadcast instead, pthread const broadcast will wake up all of the threads that are waiting. They will all get the lock in turn. They can only still have one getting the lock at a time, but they will all eventually get the lock and they will go to sleep, or they will finish up after they're done that. This is important for your lab. This is important for assignment 2. The multi-level feedback queue is also an assignment 2. Okay, we've got that. We understand what I'm saying here, yes? Good, good. We've got two kinds of scheduling policies, preemptive and non-preemptive. Non-preemptive, a synonym for this is cooperative. Processes or tasks voluntarily give up control of the thing that they have, but they don't have it taken away from them. We can compare policies on different properties. Fairness, we can calculate turnaround time, we can calculate response time, and we can say things like the round-robin scheduling policy improves the response time for tasks that enter the system, and we can say that the round-robin scheduling policy is fair because everybody will eventually get access to that shared resource. Thank you for giving me 5 minutes of your time. I will see you all tomorrow, and then I hope you have a great weekend after that. Bye, everybody.